Hi, Shohini. Thank you so much for joining us for Conversations at the Perimeter.
Thanks for having me.
Before I even ask you any questions, I just feel like I have to tell you that I've just been such a huge admirer of your work for so many years. And ever since we started talking about this show, you've been right at the top of the list of people I wanted to talk to. So I just wanted to tell you that I've been excited about this conversation ever since I heard you were coming. So
Thanks so much. You're very kind.
I'm going to add ditto to that because I remember we first met years ago, but I remember seeing your TED Talk for the first time, and now I realize that 5 million other people have seen it as well. It's pretty. There's a big community of us out there who are fans of your work.
Thank you so much, and I'm a big fan of PI, so this is great. We're a mutual appreciation society.
We're all excited today.
Yes.
So to start, I thought maybe you can just tell us about the types of problems that you're most interested in studying in your work.
Well, I have a broad range of interests, I would say, but I guess the thing that perhaps ties it all together is I'm a big fan of uncertainty. So I'm more interested in what we don't know than what we do know.
Huh.
Which in a way is kind of like being right at that boundary of what we call research, which is all, if you think about it, no matter what area you're in, it's about pushing that boundary, which is essentially what we do at Perimeter as well. So within that sort of very broad umbrella of what do we not know is a lot of stuff. In fact, most things we don't know, I think. And in physics, that obviously leads, naturally into quantum for me, where, of course, not knowing has an entirely different meaning, where the idea of uncertainty is baked into the theory itself. So that took me to a whole new level when I started out exploring this idea of uncertainty and not knowing and knowledge in general and how we describe the universe. But that, of course, also extends to questions of uncertainty about who we are and questions around identity and society. And all of that is, of course, very, very much intermingled. So all of those areas actually interest me. And that's what I focus on in various research projects now.
Thinking of uncertainty, I think when you first hear that word, you can think of it as maybe a weakness, but are there ways that we can frame this as actually a strength?
Absolutely. So this has been, I think, for me also a personal evolution where, being uncertain sometimes is absolutely worrying. There's no doubt. It would be nice if, we could predict our lives and our careers, for example, and things like this, or even what's going to happen tomorrow with the weather. But we can't actually predict any of it, and that's not necessarily a bad thing. So for me, I guess quantum has really taught me deeply that there is power to uncertainty, that the universe itself is telling us, stop with all of this precision measurements and, stop with trying to know it all. The universe is saying, yeah, let's not be know-it-alls. And that's not a bad thing in the sense that we now, of course, have started harnessing quantum uncertainty and all of these weird quantum properties that we largely ignored since the beginning of, the theory, which was developed over a century ago now, but only recently have we really started exploring and digging deeply into these stranger properties of superposition, entanglement, all of which have quantum uncertainty underlying them, and realizing that these are knobs and they are powerful tools that we can use to not only do information processing, which is, of course, the field of quantum computing, but also to dig deeper into what the universe really is, what exists, what doesn't. That to me is really, blows my mind to think about that. We actually have tools to even ask those questions, let alone answer them.
Yeah. Well, for someone who loves uncertainty, it seems like quantum is the perfect field for you to be in.
Right?
In your TED Talk, you said something that made the audience laugh. You said, if you are confused by quantum, don't worry, you're getting it, which I thought was great. It's the only field I feel like if you're confused, that means you're actually getting it. Can you elaborate on what you meant by, don't worry about the weirdness because it's sort of inherent to this field?
Absolutely. So I actually wanted to flip the script a little because I think there's, of course, other much more famous, smarter people have said that and pointed out that, you shouldn't be avoiding quantum uncertainty. It's there. If you're confused by quantum, that's, just join the club. Mm-hmm. But more in we're stuck with it kind of way, just shut up and calculate approach. Mm-hmm. But for me, I wanted to flip it and say, no, that's exciting. It's exciting to know that we cannot ignore all of this, sort of fluid universe that we live in. And perhaps we should embrace it. So that's where I was going with that.
And can you tell us what uncertainty means in the quantum context? You also use terms like entanglement and superposition, which are, those terms are, I think, at the heart of what a lot of people find so vexing about quantum theory. Can you help us get a grasp on those ideas?
Probably not, because of course, if you do, then you're not getting it.
Right.
Only
Okay.
when you're confused.
Help me lose my grasp on them.
Okay, I'll do my best. That I can do. So the theory is essentially what we call a probabilistic theory, meaning the fundamental description of any quantum particle, whether it's electrons or photons or any of these particles that we don't even see, is that we cannot actually know every quantity precisely. So if we wanted to know where it's going, then we don't know where it's located or vice versa. There's this sort of balancing act all the time. And it doesn't matter how well we try to measure, we just can't. That's really what it means to be fundamentally unknowable. Mm-hmm. All we can do is talk about the likelihood of all of these different properties.
And that's only the case in the quantum realm? That's not the case in our sort of day-to-day existence?
That's a great question, because ultimately we are made up of quantum particles,
right.
Electrons being, and then atoms and so on. So we're up the chain. And at some point, it seems like we do seem to know more precisely where we are and what we're doing to some extent. I mean, we even make GPS instruments to tell us these things, and our phones tell us even these days. So it's really that the fundamental question is, why is it that at the quantum level, there's that idea of uncertainty plays a much bigger role? It's not that we don't have uncertainty at our scale. It's just the scale is different. So at our macro scale, somehow, quantum uncertainty doesn't seem to play a role. And there are many other processes that actually, sort of wash out and wipe out quantum features such as entanglement and other cool things. And at the quantum level, if we have just these isolated particles that are not talking to the rest of the universe and we can sort of observe them and play with them, then we start seeing that these effects are big on that scale. So that's really what's happening.
You've mentioned quantum entanglement a couple of times, and I was thinking a little bit about your work before this conversation. I work in quantum matter, and I think the goal of explaining quantum entanglement is something we have in common. And I have to say, I always have a really hard time explaining it to someone outside of the field. Do you have a good way of explaining it to someone that's new to the concept?
I have some way, but this is why I cleverly said, well, if you're confused, that's fine, because then I have a way out of being too
You're hedging
clear.
your bets a little.
Right?
Yeah.
But that being said, for me, entanglement, a lot of times you hear that entanglement is about how there's some instant connection and there's something faster than light. That's not actually true. Of course, we have to be clear that there's no way to use entanglement or a connection between two quantum particles to communicate faster than light or transfer any information faster than light. So there are limits to what entanglement can do. But it is true that it's about connection between particles. That part is true. But what's really amazing, and the part that's different from, just regular connection. For example, you can think about connection as some kind of pairing, right? For example, a left glove and right glove, that's paired, or a knife and a fork. Those things are not surprising entanglement. We don't call them entangled cutlery, because actually they're not.
Well, I will from now on.
Maybe. But there is something extra about the way that connection, the pairing works at the quantum level of electrons or photons and so on. And that is that not only is there this pairing of, let's say, going back to cutlery, if one of the electrons is like a knife, the other one's a fork, sure. But what's interesting is that both of them already at the individual level have that uncertain fluid identity. So it's not clear which one is a knife, which one is a fork. In fact, they have this sort of possibility of being knife or fork, but we don't know for sure. So it's this combination where we don't know which is the knife and which is the fork, but if one is a knife, the other one's instantly a fork, and no matter where they are on opposite ends of the universe. So it's that balance between, having that probabilistic fluid identity combined with perfect connection and pairing. That's what's missing in regular knives and forks, because they are not that fluid, which is probably a good thing when you're eating, but not as powerful as quantum knives and forks, because those can be used for tools to do, novel kinds of applications and such. I don't know if that was clear or not, but that's the way I like it.
It's the first knife and fork analogy I've heard for entanglement. And I know that, this is a entanglement's a concept that has racked people's brains for a century or so, right? That we're not the only people who have been confused by it, but this bears out an experiment, and over again we see that it's a real thing. So how does that differ from superposition, which is the other sort of uniquely quantum phenomenon that you mentioned?
Well, they're connected in the sense that we typically talk about superposition as this idea of not having to choose one or the other. Superposition is the and rather than the or description, where we talk about how, maybe we should talk, instead of knife and fork, get back into maybe quantum computing language, where the knife would probably be called a 0 and the fork would be called a 1. Mm-hmm. So instead of talking about 0 or 1, we would talk about probabilities, some kind of a description that allows us to talk about probability of 0 and probability of 1. And that kind of a description, which encompasses both aspects of 0 and 1, is what we call the superposition. Right. And of course, you can have superpositions of multiple such quantum bits or qubits. And when you get to those larger superpositions, some of those types of superpositions that have this characteristic connection piece are the ones that we call entanglement. Okay. So in a way, entanglement is built into superposition. Once you allow yourself to think about superposition and describe that, entanglement naturally emerges from those descriptions, mathematically at least. Oh, wow.
You wrote a really nice article for morals and machines, and I guess the theme was kind of how quantum can help us go beyond the binary. So I really loved this article because it was teaching us lessons both within science and outside. So what are some of the ways that we can learn about non-binary thinking inspired by quantum mechanics?
Well, everything in quantum mechanics is about letting go of specifics and precision. And the idea that science and the way we think about science can impact society is not new. This is exactly what we have seen happen in society. As our science evolves, our social thinking also evolves. And for example, all of the Industrial Revolution and thinking around precisions and mass marketing and just scales of how we think about things, as well as knowing exactly one thing or another, that has all absolutely shaped the way we behave socially as well. Mm-hmm. So to me, it feels like whether we like it or not, if quantum, this whole new revolution with new quantum technologies that actually harness these, stranger properties of quantum, we're already using quantum technologies, of course, the laser and electronics, all of that is based on quantum ideas. But now we're getting to, the parts that we were kind of ignoring, like the uncertainty and entanglement. And once we start building that into our technologies and we're talking about these ideas more, it will absolutely, I think, inevitably shape this moving away, just like we move away in science from 0 or 1 and go to 0 and 1. Perhaps in society too, we will naturally start expanding our choices from right and wrong to a more, broader spectrum, and not just right or wrong, yes, no, or anytime we try to have this sort of, polar opposite kind of thinking. I think perhaps that will start evolving and we will get to newer ways and newer approaches which can influence so many aspects of our behavior, whether we're choosing what we want to eat at a restaurant versus our politics and our policies and, so many aspects of our identities that honestly, we are learning more and more are not about just one or the other. We are the intersection of so many different, environments and influences and our own, human characteristics that it feels not, if you think about it that way, it feels narrow that we've not really embraced that kind of thinking already. So Who knows?
Is that why the term revolution comes up when we talk about these quantum technologies? Because it's such a fundamentally new way of thinking?
I think so. I think it started as an idea revolution rather than about just the technology. This idea that you flip again the script of saying, let's ignore what we don't know, to let's embrace not knowing to be a tool, just like knowing is a tool. I'm not saying we ignore precision. Of course, we do need precision too. But that the combination is more powerful than, just ignoring one or the other. So I think that's the idea, the thinking of using, of embracing these as extra tools, ways that we can deeply understand the universe as well as expand on our technologies and our applications. So I think, for me, that's the revolution. And maybe it will eventually lead to a bigger revolution that I think of as a social revolution, because technologies always end up going in ways that we definitely can't control, which is a little scary, but it always changes everything.
So you would call this a quantum social revolution?
I think it will be. The question is what kind of social revolution. So one that can be, perhaps we engage in it in a more knowing way, where we understand in the history of science and technology, the way society develops hand in hand with technology gives us a lot of ways to learn how we could perhaps shape this next revolution, rather than just get caught up in the flow. We will be anyway. But what if we could actually, choose to be more structured and more, for example, deliberate and inclusive, for example, in the way we embrace and use these technologies, who has access to these technologies? That would be kind of a revolutionary approach to a technology revolution, which will then lead to a completely radical social revolution.
Yeah, you actually, it may have been in the same article that Lauren mentioned. You wrote that quantum information science, being new, it offers what you called a rare opportunity to embed inclusive practices from the start and build a responsible and sustainable roadmap for quantum computing. So I think that's what you were getting at there, in that we have a chance, because in the broad sweep of human history, quantum theory is basically a brand new thing in the past century, and we haven't quite developed our intuitions and mindsets. Do you think that's something that will come over time? Quantum will seem more natural to us, more intuitive to us, and we'll be able to build our sort of social practices around that kind of thinking?
I don't know if it'll become more intuitive, because the reality is that we are not probabilistic creatures ourselves, in the sense that our thinking is actually, because we're pretty vague often. Right? We're not always about the way we would perhaps imagine a true artificial intelligence based on binary computing, yes and no kind of choices. We don't actually think that way. So we do naturally already have some of these qualities, but we don't consciously acknowledge them. So perhaps that part will become more natural, where we allow ourselves to explore our thinking and how we make decisions and how we behave using this kind of a framework. But whether or not that will be more intuitive, I don't know.
Right.
But perhaps it will become more widespread.
Yeah. And can you think of examples of how we could, in the field of quantum computing, develop the field in a way that's more inclusive and sort of egalitarian than, let's say, an older branch of science like chemistry or something like that?
Sure, absolutely. In fact, that's part of what I wanted to write that article for. Often what we do with technology, especially on the science side, and I'm sure we've all been guilty of it, is that we're so curious. We're like, let's just try it and see what happens. What if we did this? What if we tweak this knob? What if we build this thing? Which is fun, because we are inherently curious, which is wonderful. But what if we could ask the what if questions and also include those who ask what will happen next? Because that too is a creative process, because we can't quite predict it until it happens. So, and humans are very unpredictable. So maybe we learn more about how to predict human behavior too in the future. But for now, there are experts who understand human behavior perhaps just the way I study physics and the laws of physics. There's, others who study social sciences and things like, identity and inclusion. And often me as a physicist would perhaps not think that they should be part of whatever is the research project I'm doing to build this new quantum application to do something with healthcare or so on. Right. But healthcare would impact humans. So perhaps we should get some human experts into that kind of research and development. So that's one example of where we could be more deliberate. As we develop the technology, we don't have to limit what we do, but we should ask, what's the impact? Who's using it? Why are we doing this? Where will it lead? What's the environmental kinds of concerns we have? Is it sustainable? There's so many other questions that we don't typically ask all at the same time.
Yeah.
Eventually get to it, but wouldn't it be nice if we could do that in a more structured fashion?
So the Industrial Revolution, we know that it essentially built the 20th century and into the 21st century, but it had some serious repercussions for our environment and for our health. Some good, lots bad. Are you sort of proposing that quantum information is a field that's so young that it would kind of be like going back to the start of the Industrial Revolution and saying, we could plan ahead a little bit better and have fewer of the negative repercussions? Do we have the wisdom of hindsight now with a new revolution that's starting?
That's exactly the kind of what-if game that would be great to play.
Mhm.
What if we could go back to the beginning of the Industrial Revolution and make a few decisions, key decisions? What would we have decided?
Mm-hmm.
Knowing everything we know now, what would we have done different? And from that kind of an exercise, can we learn something about starting this new revolution and ask, what if we use those kinds of lessons to try to put into place whatever are those key decisions and policies? It would require obviously some kind of ability to predict where we're going,
Mm-hmm.
and we'll never get that right because there's just no way.
But history does have some guidance for us.
Exactly.
Yeah.
Right now, our approach is we don't even look back at history. We know Industrial Revolution happened, but that's about it.
Mhm.
We don't really take it as a lesson that we now use for the future. There are, as I said, expert scholars who do actually think about history, think about political science and their causalities and correlations. So I think it's happening, but we don't necessarily then include that as we roll out the technology itself.
Mhm.
So it's all being done in silos, which has always been kind of a problem with research. So here's a chance for us to break those silos.
Mhm.
Are there particular tips or strategies that you think the leaders and developers of these technologies should have in mind as they roll out new devices?
Well, if there's a leader who's in a policy meeting, first things first, look around the table. Who's at the table and who's missing? That would be number one step.
Mhm.
And it's amazing how much you can learn just from that alone. Because I don't think there's going to be one person who will be able to make all the right decisions. So find the team that can really bring in all of the skills and the expertise you might want to, think about at least, and then go
Mhm.
from there. So,
Break out of those silos.
for example, yeah. So I don't have all the answers, so that's part of the problem. I would want to look around the table and say, who would I collect to answer all these wonderful questions? But
Mhm.
just right now, in the few minutes we've been talking, we've had so many questions that I feel like would need a lot of time to even explore and understand how we would go about actually rolling out a more
Mhm.
deliberate approach to technology. And it doesn't have to be just quantum. Quantum is one example
Mhm.
where it's a young field, so we have that chance. But so is machine learning. And they're probably going to intersect. They already are to some level. So this could be something that becomes a framework of how we, as a society, engage with technology going forward.
Mhm. In this conversation, we've been using the word identity many times. I think you first started talking about the identity of a fork or a knife or a spoon. And then, of course, we can also think of this in a more personal context. But it seems like this is a pretty fundamental word to a lot of the things that you're thinking about. Can you tell us a little bit more about identity and why you think it's so important to be considering?
Of course. And you're absolutely right. It's something that's central in both to the physical world that we interact and to our social spaces, and just more broadly everywhere. Whatever we do, it's about how we interact with, whether it's other human beings or with other objects or with, thinking, even our imaginations and even things that are not there, that don't exist. Right? Everything is about that interaction and then engagement. And that has everything to do with who we are and what shapes us. So to me, it is really an important piece that connects many of the sort of projects that I work on personally, where other than physics, I do think a lot about who I am too as a person, because, whenever we meet new people and we introduce ourselves, we say, hi, my name is so-and-so, and I am such and such, right? And who am I, right? For one thing, the fact that am is the key word is already interesting. Instead of
Right.
telling people what I do or what I love or what I'm interested in, we always lead with this is what I am, which honestly seems like, again, one of these very, very known concepts where somehow I'm supposed to already know that.
Yeah.
I am. There's no room for uncertainty there. I am such and such. So this is what I mean. It's built in, this idea of knowing everything. So questioning that automatically means questioning not just my own identity, but what does society mean about who I am, and whether I'm a physicist, or let's say I'm an immigrant to Canada, or a woman, or a certain age, or I have certain, I have a certain abilities, whether I'm healthy, or if I, whether I have, there's so many things. I can't even think about all the different identities we have. So to me, it's important to explore that, and it can't really be separated out and say, okay, here I do physics here, and then I think about identity here. To me, they must connect, and they always do.
Mm-hmm.
That's funny. It's interesting because I think a traditional look at science would say there's the science in one department, one compartment of your life, and then there's the rest, the personal stuff. And at what point in your life or career did you realize that they're not separate domains, that they're intermingled like that and evolving over time?
I started absolutely traditionally, as you described, as in thinking about everything very separately. And, when I was a student, a grad student physics, and I've talked about this often, where I did notice that it was kind of lonely because there weren't that many women in the room, and there were certainly not many people of color. I did all of my grad studies in the US, in the Midwest. So, but back then I thought, okay, who cares? That's not relevant. I'm in a physics classroom. I'm doing physics work. So if I do great physics, nothing else is relevant, leave alone being important at all. So that was my approach, that if I do physics, that's going to be everything. And if all I can do is really great physics, then everything else will solve itself. And it took a long time for me to eventually realize that it's not just about whether I do good physics or not, because it's not, who I am and how I'm perceived does matter. And it's not necessarily always even a level playing field in terms of how your work is perceived or not. So even if I do great work, perhaps, it won't really get acknowledged, depending on, who we are and who's there, and the fact that there are a few women, and there's challenges, absolutely systemic barriers and challenges and biases that we all have that impact how we can do our physics or whatever other area that we're talking about. So that's how it started evolving, where I'm like, okay, I'm forced to face it in my own career and my own life. And then I realized that it's not just me alone. So the more I thought about it, the more I'm like, I don't know much about what it means to be a woman or a physicist and all of these identity questions. I'm not an expert on any of that. And all universities do exactly what you described, which is separate out. Okay, you go into the arts degree or the science degree, everything is very separate. So I didn't know students who were able to discuss these kinds of questions, and we're told to ignore it. So I was a very well-programmed science student. It took a while to break out and realize, well, maybe I should go find others who know more about this, which, it didn't happen until my early days as a junior faculty member, that I got to interact with other researchers from other faculties who were in psychology, social science, gender studies, and that really opened my eyes. And I realized, yes, there's research, there's expertise, I can understand more about these kinds of questions of context. And it went from there to eventually realizing, all of that, I have to deprogram myself and, try to think more holistically. And it does align with my physics in the sense that that's what I'm doing already in quantum, where I'm deprogramming from the, 0 or 1 and trying to embrace this new framework of computing, a new way of thinking, which could absolutely be expanded to new ways of being broader in intersecting all of these different aspects. So that was the way it all happened.
Wow.
Well, we also had a question that was sent in about how you find this balance in your work, or how you incorporate some of these different ideas at the same time. So this question was sent in by Priyal Bordia, who just completed her undergraduate degree in physics from Mumbai University. She asked, being a physicist and a strong advocate of inclusion, diversity, equity, and accessibility, what were or are the challenges that you faced or are still facing to maintain balance between the different types of work that you do?
Great question. So I'll answer by saying I don't see it necessarily as a balance, as in there's some ideal proportion of 30% of this and 70% of that, or on Tuesday it's that, and then Wednesday it's something else.
That's the urge for certainty that is contrary to the quantum urge. Yeah.
Exactly. So for me, and this kind of leads into similar kinds of questions come up with work-life balance, because I don't see my work really as work-life balance because it's all work to me, but so I don't have balance, in other words. It's this idea of here's a bar, we've already decided it, we've set it because we know it, and now we'll all try to strive for it, which bars are great, but I think of bars as aspirational, to be honest, which is we all need aspirations. But, reality is much more messy, which to me exactly aligns with reality is much more fluid. So going forward, to me, it's not about thinking, well, did I achieve the balance now between the physics thing and, gender identity question or anything like that? Because they're so mixed together, they're a superposition. I'm sorry, I just had to go there. And balance to me is about whatever feels right. So my bar is really not about whether things are in proportion. My bar is, am I achieving my goals of what I would set as this is where I want to be? What's my purpose? Where do I want to go? What do I want to do? And does it satisfy me? Mm-hmm. So those are my ways of trying to evaluate and assess where I want to be rather than go for that balance question.
Mm-hmm.
Well, directly related to that, we do have a question from a young woman named Summer. So could we play that?
Hi, Shohini. I'm Summer from Waterloo, and I'm wondering if you have words of inspiration for young women looking to pursue an exciting career in science.
Wow, thanks, Summer. I'm not sure about what would be an inspiring thing to say, but I can say that in my own life, as I just mentioned, I switched away from trying to think about who I am to what I want to do. Mm-hmm. So I would suggest, think about that. What do you want to do? Is it something that you feel you can contribute something? Will it help the world in some way? Even better. And are you good at it? Then even better. If you can put those three things together as you follow a career in science, then I think you will find a very satisfying project perhaps, or somebody who you can talk to that would help with those kinds of questions and lead you, or an example where you're like, yeah, they did something that's really great. I want to do that rather than I want to be that. So that's one thing I would say. And the other thing is, as a scientist, in a career in science, myself, being, a woman and a person of color, these have been, of course, important. But I want to tell everybody who's out there who's feeling like I did often in classes where I'm alone, I would say you are actually not alone. And I remember hearing this actually in a conference, somebody else mentioned that, if all of the so-called minorities in science or, any other fields got together, they're really no longer a minority, right? So often we feel like we're the only ones who are feeling that way, and we feel isolated. Loneliness and isolation can be two of the biggest factors that make us stop following our dreams and our goals. And in science, for sure, that happens a lot when you don't see others like you. So my message is that, in fact, you are not alone. It's not you. It's just that we have to do better and build that inclusive community that I keep talking about. But you can be part of it. I hope that's inspirational.
Looking back on your own journey towards being the physicist that you are now, how did you make the decision to pursue this career path?
Well, when I was a kid, I was always curious. I was exactly that kid who loved Star Trek. I mean, that show, man, that must have influenced so many kids like me.
There are a lot of scientists at Perimeter who have said the same thing.
Right?
Yes.
Isn't that incredible? I want to just, I hope that, I think they know the Star Trek crew, right? But, I once went and talked also to, this is a bit of a digression, but I had a little chat with Neil Gaiman, who is the author of the Sandman show, which is now, it's now a TV show, but back in the day when I was a grad student, when I would get very stressed, I read the Sandman comics, right? And so I had this chance to talk to Neil Gaiman, and I said, thank you, Neil Gaiman, you got me through my PhD. And he was so amazed because he knew that, of course, he had a lot of fans, no doubt, but he really felt that, being able to help with keeping me on track in science, that was really something that he really enjoyed hearing. So I feel like we should tell the Star Trek creators how many people have got into science because of them.
What resonated about Star Trek? And was there a character or a storyline that stuck in your mind? And
it was this vision, just the idea that human beings all together with, just being, working together. Each person on the crew had their own contribution they made. So there was always something where sometimes it was, Sulu, and sometimes it was Spock and, Kirk and so on. Well, Kirk was always the leader, but everybody did have a role to play. And of course, being able to see that such a variety of different activities happening in space and being able to transcend all of our limited sorts of, worries on Earth and be able to leave it all behind and think that big. To me, that idea was just wonderful. And I would just sit there with my jaw on the floor most of the time, no matter what the show was about. It was just that being able to share in that was really special.
And how about deciding to pursue quantum? Was that also somehow sparked from Star Trek, that you decided to explore
did you want
quantum?
to teleport people? Beam them up?
I had no idea. One day I'd be able to sit somewhere and say, yeah, I just wrote this paper about teleportation. I mean, oh my gosh, if I could tell my younger self that, that would be
What would she think if her older self said, oh, you're studying teleportation for real?
Yeah, you're an alien from a future world, trying to trick me into something.
That's the Star Trek skepticism.
Exactly.
Yeah.
But no, I think that for me, quantum, of course, was not connected back to when I was a kid. I did do a summer project as an undergraduate, and I highly recommend that if you can get a chance, if you're an undergraduate student and you want to, explore what science is all about, then summer project is great because in class you learn a lot, sure, but you don't get to explore on your own. You don't get to dip your toes into these waters where you don't quite know the answer. Mm-hmm. So this is, again, for me, perhaps that's the moment where I started really understanding, not knowing is really fun for me, because I didn't know anything in that project. My professor was super patient. He gave me this calculation to do. Later on, I realized it was about, these particular, a particular quantum Hamiltonian and so on. I didn't even know what any of that meant. I was just calculating blindly, but I kind of had to get the code to work and calculate something. And I knew there was a new thing, and eventually it would be used to understand something about electrons and so on. So that was my first taste of quantum, and I could do the calculation. So my professor suggested that I should perhaps think about grad school in quantum. And that's how it started. And once I was in, I'm like, well, yeah, this is for me. Nobody knows anything, and you're supposed to not know things. So, obvious.
You're starting on the right foot.
Well, we had another question that was sent in, kind of how your research has evolved since that time. And this one was actually sent in by a former student of yours and a former podcast guest of ours, Meenu Kumari, who's a postdoctoral researcher here at Perimeter.
Hi, Shohini. This is Meenu. My question is related to your PhD and postdoc times. Given the current revival of the field of quantum chaos in multiple contexts, would you like to briefly tell us a bit about your fundamental research in quantum chaos in your PhD and postdoc? It would also be great if you could first recount how you started working in this field in your PhD in the first place. Thank you.
Thanks, Meenu. I'll start with the last question, is how I started. So in grad school, I was working on this one project. Again, when you start, you don't quite know what you're doing. So my professor, this was my graduate school professor, Ivan Deutsch, who was my PhD supervisor, he said, why don't you, explore this one system that we've been thinking about for a long time? It has to do with an electron, again, in a particular sort of, system controlled with certain magnets and lasers and so on. Why don't you model it and try to understand what's quantum about it? And in order to understand when something is quantum, you want to compare it to when it's not quantum, really. So his project to me was, why don't you model it, but not as a quantum particle? Model it as just a regular, what we call a classical model. So that's what I did. I went and wrote down the model, and I started coding it up, trying to see what would the behavior be, what would the trajectories look like as this electron feels all these forces, but just as a classical, a pretend model, really, of classicality. And it wouldn't work. My code, no matter what I did, I kept getting this weird sort of, everything looked random all the time. And when I changed something small, everything again changed a lot. I had no idea. It didn't strike me that, of course, that is the signature of chaos. When you change something very small, it's like the butterfly flaps its wings and then you get these storms. That's really what I was seeing, but I didn't know it. And luckily, when I showed it to my supervisor, there was somebody else in the team who was able to recognize and say, oh, are you sure that's not chaos? So that's how it started. And then, of course, I went and learned all about it. And indeed, it was chaos. And for me, that became such a key question to me. What's quantum about quantum? So over the years, the systems I studied to understand chaos have evolved. Turns out it's still one of the open questions in quantum, as in we don't quite know why we have this phenomenon that we see in the weather patterns and so on at our macro level, but we don't quite know how it manifests at the quantum level, or if it does at all. Right. So that's a pretty big thing not to know. And see, I'm like, wow, a big thing that's unknown. This is like a magnet for me. So,
that's amazing.
Yeah. And so that's why I continued in that area. And my next step was to try to think of how can we actually even study some of this in the lab rather than just do the calculations and simulate it. And luckily at the time, my supervisor, Ivan Deutsch, was working quite closely with an experimental group led by Paul Jessen at the University of Arizona. So that's how I got connected to that group. And over the years, we ended up developing an experiment to try to see what happens when you have these individual electrons that are evolving in this particular model that I had already modeled classically. So classically, we saw this chaotic behavior. Question is, could we see any glimpse of that at the quantum level in the actual experiment? And it turns out it's, of course, quite difficult. For me, it was easy. I could just change some numbers on the computer. But to map that into an experiment and do it, of course, took a lot of time and effort. And the group at Arizona was amazing. But eventually we did. We did an experiment where we could actually observe, almost like we took photos of this, individual electrons that were evolving in this particular controlled sort of Hamiltonian, which is really just a fancy word for a control system where we control all the lasers and magnets. So we took photos or images, really, not real photos, but a way to make a photo of what this system is doing. And then you overlay all the photos at different times and put them all together, and it's a movie. So we watched this atom evolve, under whatever these controlled fields were, and it did actually reflect this chaotic behavior. Wow. So it was just wonderful to see that, and that was the first time anybody had seen that kind of chaos. So
that's so cool.
Yeah. And after that, of course, that became sort of my central focus area, and I'm still working in questions on quantum chaos and different types of systems and, different kinds of questions around, what happens when we try to characterize something like entanglement, which we think of as a quantum thing. What happens to entanglement when we think about a chaotic system where there's all of this at the macro level, but entanglement doesn't have a classical analog. So would it have this classical chaotic signature at all? Mm-hmm. And these are open questions. And actually with Minu, we've learned a lot about these kinds of systems. And she's herself discovered these lovely sort of ways to think about entanglement and chaos and how they're connected. And there's definitely relationships. So we're trying to generalize some of that.
When I was rewatching your TED Talk, I jotted down a few of my favorite lines, and this is related to just the enthusiasm that you speak about this stuff with. You said, "It's a lot of fun being a quantum physicist. I highly recommend it," which got a nice laugh from the audience. But can you elaborate on that? Like, where is the fun in what seems like really difficult? There's math and there's coding and there's experiments, and the line about recommending it. Do you recommend it to anyone, or does it take a certain type of person to want to dive into this certain type of fun?
Well, I think there's one common fundamental requirement. If you want to do quantum, I guess maybe it's even beyond quantum, but definitely for quantum, since that's my area. You got to be curious, and you have to be okay with not knowing everything. As in, you have to be okay with being right at the edge and being frustrated often because our limited, minds where we keep seeking intuition, it really isn't there. But so if you happen to be the kind of person who likes that kind of mystery, then I feel like this would be a good area for you. But, fundamentally, yes, is there math involved? Of course. Do you have to do a lot of learning? Sure. But, if you wanted to, let's say, be a ballet dancer, it's not like you're not going to have to put in the work. It's not all fun. Nothing. I mean, it looks beautiful in the end. You want to play basketball, that's fun too. But guess what? You really want to play it well, you got to do the work.
Yeah.
So absolutely, you have to do the work. And this is why it's important to find that area, whether it's quantum or something else, find the area that you know where you want to go with it. What's the purpose? Why did you choose that field? Because then when it gets hard and you fail, which you will often in almost every field, certainly quantum, you're going to have that energy to get up again. Because you know what your passion is. So that's why people talk a lot about passion, because passion is what makes you get over failure.
So you've hit dead ends and had failures, and
it happens a lot. So
more than success.
Yeah, we write all of our papers and do the presentation that talks about these rare moments of success, like watching those movies. We don't write about the 6 years of movie after movie where all you see is darkness.
Yep.
Imagine papers like that. I feel like we should have that.
The Journal of Failed Experiments.
That would be great.
Big journal.
I know, right?
I sometimes think we should write about those more, though, because sometimes it can actually save another person work, first of all, but it also can be inspiring to see how long it actually takes to see the success.
I think so. At least we should do a summary. In every talk, we should have one slide of this is everything that we went through, and this was the level of pain. We should have a little bar,
scale.
right? A scale. There it was. Everybody's scale would max out, I think.
Yeah.
I would love it if in one of your talks you just started with a movie that was just darkness.
That's such a good idea. Maybe I will. Thank you.
So for you, what's the equivalent of the ballet dancer actually dancing, or the basketball player, playing, shooting the winning basket? Like, what's the equivalent for a quantum scientist in terms of the fun?
The fun is seeing that non-dark movie.
Yeah.
When you do it.
When it works.
Often it's, I was lucky that it was actually a movie, but, often it's one little number or something you calculate, or a little plot which, goes just slightly up rather than down. Those are the moments. And then there are also these other unexpected moments. So one time I'd given this student a calculation to do, and they came back with the calculation, and it looked completely wrong from what I had expected would be the plot that he showed me. I'm like, are you sure that's even correct? Oh, wait, it's obviously wrong. Go and check it again. So I checked and came back like, it's actually correct. I can prove it. Here it is. And turns out it was correct. And it was unexpected because, again, the intuition that I had about what to expect was completely wrong. And what he found was, in fact, so interesting because it was not what we expected that we wrote a whole paper about that and why it was completely different. So those moments are just fabulous too.
I can see your face light up when you talk about
Yes, because those are very rare. But boy, the days and months or years of not getting anywhere, all of it becomes worth it when that happens.
And Shohini, in addition to being a professor in working in this quantum research, you're also the director of the Laurier Center for Women in Science. Can you tell us a little bit about this center and what the goals are for it?
Sure. So this center, again, arose from this evolution in my own personal journey, where I realized that to really be engaged in, good science, I have to also engage in understanding my own identity, the context of science, and things like this. So the center is unique in that we wanted to bring together scientists like me, and not just in physics, but in all of the natural sciences, with social scientists who did think about questions like gender, identity. And this one focused on women in science, just because that was an area that, there were a lot of researchers that I knew were in the field, so we brought them in. And it was about bringing those two pieces that were usually siloed together and getting new conversations started, and then developing, science, scholarship-based initiatives to try to be more inclusive and find out what the problems are, and then address them going forward. So that's what we've been doing in the center.
And what are some of the key problems you've identified and some of the solutions you've been working towards?
Okay, so key problems turn out to not be about what we've been focused on actually for a long time is how can we do things like girls' camps or, outreach that interests girls in science. Turns out girls are quite interested in science. And then there's all the math camps to try to make girls better at math. But girls actually are outperforming boys at math. And we're still having math camps for girls. So what we found is that the initiatives are often not aligned with what is a real problem.
Mm-hmm.
So similarly with things like mentoring, women are over mentored, to be honest, right now, because it's all about let's help and support them somehow, when it's not that that's what's missing. It's about, is the system at providing enough opportunities in an equal way? No amount of mentoring will help if already there's a totally skewed sort of system where there's no way for a woman to climb beyond a certain point or anything like this. So really what the discovery was that there are all kinds of systemic and barriers and biases that are not being focused on. On the other hand, all the initiatives were more about fixing the women rather than fixing the system. So our big motto became fix the system, not the women. I think that applies to everything that we do. We are doing mentoring, but framing it as something that's really about adapting to a system that is flawed. So until the system is fixed, of course, we need more of that mentoring, and we need to have that extra help and support that's missing because everybody's not starting at the same point and given the same push. So that's why we are addressing these questions. But the long-term goal is fix the system, which is why we were involved in things like Canada's Dimensions Charter, which is about a systemic evaluation across Canada and trying to build policies and a culture of change rather than just individual help. So yeah, that's where we're going.
And this problem of building a culture of change, I think it can sometimes feel very overwhelming and hard to know exactly what to do. But I know for myself, sometimes some of the moments that have felt most inspiring is when I realized that just a very simple change that I could make, writing something differently on a course outline or something like this, which I can very easily do, can actually have a big impact on some students that I'm working with or something. Are there any small things like that any theoretical physicist could implement to make academic environments a little bit more inclusive?
So many. Where to start? We do actually have lists, and I'm happy to provide them. But for example, to build on what you were saying about small changes in the classroom, if you were to open any physics textbook today and look for names of physicists, you'd find Newton and Einstein and perhaps Bohr, and there are many names, Maxwell. You will never find a single woman's name. Not even Marie Curie is actually included in physics textbooks, perhaps in chemistry textbooks, but not physics. So there are zero names. So that's one thing that as an educator, if you happen to be teaching a course, if you look at the topic you're teaching and do a little bit of digging, it'll be amazing how many women have contributed who are not being mentioned at all. And there's so much inspiration to be had in their stories because typically they did it, while they were facing many challenges and biases. So that's something that can be done that we can all work on. As a researcher, one thing that I've been doing in my own papers is there's always an acknowledgement section that we put in where we thank people who are involved in it. And I put in a land acknowledgement so that it's documented that we are, on this land of indigenous peoples. So I think that's something we could all do. Imagine how many research papers are submitted and published every single day. Imagine if we all did that. That's true documentation. Goes beyond, just what we do today because it's in the record. It's a legacy. So that's another example where it takes zero effort, really zero. Once you have it, you put it into all of your papers. So there are small things like this that can be done. As I said, we could have an entire discussion just about that, but maybe I'll leave it there.
Well, this seems like maybe a good time to mention the book that you're working on. Can you tell us about that project?
Yes, so my own effort to exactly do my part to tell these stories about all the women who have been ignored is to sit down and write about them. So for the pandemic, that's been my big project.
That's your lockdown activity?
It's the kind of thing where, I can do it by myself. So that was good. But I felt like I wasn't alone doing it, just because all these women that I was writing about and researching, they seemed to be there all the time. It was really actually very inspirational and the best therapy. So another thing that I recommend. So I have I've been writing about all these women physicists who, some of them have we know, if you happen to be in the field, but they're not widely known the way, we know Einstein or, Newton and so on. So I wanted to tell their stories, not just the science they did, but also the context and the fact that a lot of their experiences are still relevant today. So I approach it through my own experiences. So that's what the book is about, and it's going to be published next year. And I hope lots of people know about lots of women from all around the world who've actually transformed physics.
Without any spoilers, could you maybe tell us about one particular woman that you learned about in this process that maybe you didn't know much about, and just a story that really resonated with you?
Well, being born and raised in India, when I was a student, I had never heard about this woman. And even until quite late in my own career, because I engage a lot with trying to understand women role models and trying to find them, that's how I got to know about this woman. But she's really not that well known as yet, a little more than before. And her name is Bibha Chaudhary. And it's amazing to me because she's actually Bengali like I am. She's from Bengal. And she has this incredible story because she was born and raised and did most of her work while India was still a colony, British colony. So in that context, she got a PhD in physics, worked with 2 different Nobel Prize winners, was involved in the discovery of 2 different fundamental particles in nature, never got acknowledgement for any of it, but she published like 4 different articles in Nature itself, the journal, which is unheard of even today to have that many. And she just published them back to back. I know. So, she was really an incredible person. And, it somehow didn't seem to bother her that, she didn't get the kind of acknowledgement and recognition that others are getting for work that she herself was doing. So, and that was, of course, a very common thing, unfortunately. But that combined with the context of India, under British rule and lack of funding, lack of support, lack of infrastructure, and yet there she was discovering everything about the universe. It was really amazing.
Wow.
And all the women have these kinds of huge stories. We're not talking about small discoveries. Discoveries at that level that we just don't celebrate, which doesn't make sense. Imagine being a little girl growing up in India and not knowing this woman's name. It's mind-boggling.
Does the book have a title yet?
It does. The working title is Invisible, but in parentheses, because of course it's about shining a light on all these invisible discoveries.
So as you said, many of these scientists have been invisible for many years, but I guess there's also many other women who could have been amazing scientists who didn't get to because of the systems that we have. So do you have hope that this is going to change in the future, that there can be more women that can benefit all of us?
I absolutely have hope. But I know that the numbers are quite flat in the sense that we haven't seen much of an increase over the last decade. There's been some, but at the rate we're going, we're talking about a century or more before we even get to equal numbers of women at higher ranks. And the thing is, it takes time, of course. So, for example, right now we know in Canada at least that we're roughly at about 20% of high school students who are, when they choose what major they want, about 20% choose physics. So, that's kind of the number we are. But that means that 10, 20 years later, the professors in Canada, at max, unless we get many from outside, at max, we're going to have 20% of our physics professors are going to be women, which is 1 in 5. And that will be 20 years later. So this is why it'll take about a century to really have everything move through the system. So we need to start now, and we need to do it better than what we're doing now. As in, yes, is it changing? Yes, but not fast enough.
You mentioned the need not for more mentoring for girls and young women, but for the system to change. With the efforts that's being put into this sort of systematic change, do you think we're seeing that timeline shrink ideally between now and when we can see a real positive, tangible difference?
I hope so, but I feel like as we've been talking throughout our conversation, we can't just say this one thing or that one thing is
Right.
specifically what will help or not. It's a mixture of so many different factors, including all of the influences on young girls and boys from outside of even physics, right? Back when they start picking up their toys, or go to any toy store and go look at the girls section and compare it to the boys section, they're not the same. It makes no sense why they should be different, but they are. So until we can change all the toy stores, all the bookstores, what we see on TV, what we are doing in gatherings, how parents are interacting with their kids, there's just so many pieces. Until we can change all of that, we're not really going to address the issue. So is it possible to speed it up? It's very difficult, let's put it that way. But that doesn't mean we'll give up, of course.
Right.
Mm-hmm.
It's an unsolved problem, like you enjoy. There's
Of
uncertainty,
course,
so you're.
it's big and,
Yeah.
and hard and challenging. I'm in.
That's amazing.
Yeah, I had been planning to ask you how you stay motivated for such a difficult and frustrating problem that this is, but I think we have the answer. You love uncertainty and you love hard problems. So
And also, I think every single young person who can take one more step towards that, to me, is a success. So sometimes I'll get an email from somebody who says, "Oh, I think I want to do more of what you were talking about." That to me is it's like having turbo engines. It keeps you going. So yeah, that's really important. One person at a time. We're gonna get there.
yeah. Well, I really love seeing some of the lessons that you've been able to share that really come from the intersection of making environments more inclusive, but also your quantum work. We talked about how this can teach us about not being susceptible to binary thinking. I know you also, in one of your talks, talked about how the universe doesn't care about gender, so we shouldn't either, things like this. Are there any other unique lessons that you've really only been able to learn because of working at this intersection?
There's no such thing as failure. The good thing when everything is uncertain is that there's no real failure. Because failure itself, either it means you've discovered something new because something old has failed, or you've discovered that, there's no one thing that is success. So either you'll have to try to go around whatever is the barrier, because, yeah, that's a real failure and it just won't work. But that means you have to adapt. Or it means that maybe there's just not one answer. There's more than one. So to me, that's been also another really great lesson, as in failure just rolls off now. As in, you want me to another failure? Yay. I'll celebrate it. As you said, we should have that as a slide in all of our presentations, or I'll start showing the failure movie or something.
It makes the success more exciting.
Yeah.
Celebrate the failure, I
Yeah.
say. That's a good one.
Amazing.
You also do a lot of this kind of thing where you talk about science to audiences that are not scientists. And why do you do so much of that?
Couple of reasons. Firstly, I feel like there's so many exciting things in physics that I've learned myself. That feels like a big secret if I don't talk about it, right? So it's almost like I can't stop talking about it, which is probably not a good thing in some situations.
It's perfect for this situation.
You're a captive audience, but often, you say, "Hi, I'm so-and-so," whatever. You're at a bar and say, "Hi, and I'm doing physics," and people will turn around and run away. So it's not always that I talk about it. But I think it is important to not just talk to fellow physicists, of course, because, yeah, we all get it. We start from the assumption that I'm not the only one who gets this excited and giddy about physics. In fact, everybody in physics is kind of like that. We just don't show it because when we give our talks, we're very objective and, yeah. I don't know why, because, I'd prefer to be just excited all the time. But this is where we start from. Already that assumption that we're all super into it and we really want to learn more about the universe. But perhaps somebody outside physics doesn't get it, as in, why are these dry equations so important or interesting? And that's why I think it's important to tell the story behind those equations and the story of who we are, why do we do physics, and how do we do it in ways that are about its relevance and how it connects to our everyday lives too. Because it is one of the really unifying things. We're all part of the same universe. So the more we know, the more it helps us, know ourselves too. So I feel like that's the reason that it's important to get everybody engaged. And not to mention, we've just seen throughout the pandemic the importance of really understanding science and making decisions, and also knowing how to be critically thinking about it. What's the good science? What's the bad science? All of that can only happen if we reach outside of our own communities. So yeah, to me, it's a critical piece.
Mm-hmm. Well, Shohini, thank you so much for sitting down with us today. This has been an amazing conversation. Thank you so much for sharing your time with us.
Thank you. I had a lot of fun.